Hey, my name is Austin Hutchison, and this is my video report for Lab 1. A little introduction. The purpose of this lab was to use tape to observe how charged objects interact with their surroundings and with one another, and then to develop a computational model using Python to estimate the fraction of atoms in one piece of tape that gave up an electron when they were ripped apart. Little preview of the results. I observed that the like-charged pieces of tape repel one another as expected, and I calculated that the ratio of excess electrons to total atoms in the tape was 1.60 times 10 to the negative 7. Some of the main fundamental physical principles used in this lab are Coulomb's law, which gives us an equation for the electric force between two objects, which obviously we use in this lab to calculate the force between the two charged tapes. And then Coulomb's constant, which is 9 times 10 to the ninth, obviously used in the Coulomb's law equation up here. And finally, the gravitational force formula, which is F-grav is equal to mass times gravity, which we use to find the gravitational force on the floating tape, which counteracts the electric force. Now about the actual experiment. The system in this was tape 2, or tape B in the picture over here. It's just the one on top. The surroundings would be tape 1, or the bottom tape, which exerts an electric force upwards on tape 2, and then of course the Earth, which exerts a gravitational force on tape 2, pulling it downwards. Initially, both pieces of tape are electrically neutral, but they're given a charge by transferring electrons to them after they are ripped for another piece of tape that's stuck to the table. And then initially, or at the start of the experiment, tape 1 possesses a charge of Q1, tape 2 has a charge of Q2, which are unknown right now. But when tape 2 starts floating, the observed separation distance between the two tapes is 2.5 centimeters. Now for my model in GlowScript, a couple of assumptions we had to make in order to model this situation on a computer was to assume that each piece of tape possessed about the same charge, and we had to treat each piece of tape as if all its charge and mass were concentrated at a single point, because obviously it'd be very difficult to model the actual shape of the tape. Here in my model, you can see I just a bunch of given constants, as well as constants that I measured, just things about the tape, and obviously the length of an atom here, which we use later, and then a function here which is used to define an electric field. Now continuing with the model, here you can see I just defined the spheres that represent the two tapes as a point charge. Obviously gave them an identical charge Q, and defined the gravitational force on tape 2 up here, and then also modeled the electric force as an arrow that has the same magnitude as the gravitational force, because tape 2 is not moving, it's just floating, so all the forces on it have to cancel out. This equation right here, line 31, I rearranged the Coulomb's law equation knowing that Q1 and Q2 are the same. I rearranged that equation to find an equation for Q in terms of all the other variables. And then here I found the charge Q and divided it by the charge of an electron to find the number of excess electrons in tape 2, obviously, which you can see here in the output terminal. And then the ratio of excess electrons, or I found the number of atoms on the surface of the tape by dividing the area of the tape by the area of an atom, and obviously found that right here. And for the results, I found that when tape 2 is floating, the forces on it are balanced, so obviously the magnitudes of the electric force and gravitational force are equal. I found that the ratio of excess electrons to total atoms in the tape was 1.60 times 10 to the negative 7th, meaning that 0.00016% of the atoms in the tape released electrons. Some differences between the experiment and the model. In reality, the charges are not exactly equal. The charge is spread around the surface of the tape rather than concentrated at a single point, and the model does not account for other forces such as air resistance. Some additional sources of error were accidental interaction with neutral objects, which will result in discharging of the tapes, and also I estimated the mass of the tape using its length instead of an actual scale. Now onto the discussion questions. What if electrons had positive charge and protons had negative charge? What we observed would not change. Each tape would still end up possessing the same type of charge, so they would still repel one another regardless of the charge sign. Why is it important to handle the charged tape as little as possible? They could come into contact with other objects or your hands and could end up losing some of their charge. They will always try to neutralize themselves in any way they can and will release electrons to other surfaces which would discharge them. Yeah, that's it. Thank you for watching.